We have been exploring the concept of influence coefficients, and now we will delve into how these principles apply with systems of multiple degree of freedom. As we have seen in previous examples, influence coefficients are powerful tools for understanding how forces and displacements interact with a mechanical system. Hence, understanding this influence coefficient in multi-degree of freedom system is crucial for analyzing the behavior of complex structures and machines under various loading conditions. They provide a fundamental way to quantify the relationship between forces and displacements in these systems, paving the way for more advanced analysis in dynamics and structural mechanics. This lecture is brought to you by Dr. C. Sindhamarikannan, Associate Professor in the Department of Mechanical Engineering at SVC. Let me continue with some problems. In the world of mechanical systems, understanding how forces and displacements relate to each other is very much important. Today, we will delve into concept of influence coefficient using this example. We have a system of three masses 4m, 2m and m connected by springs with stiffnesses 3k, k and k itself. Our goal is to determine the influence coefficient for these systems. This coefficient essentially tells us how much each mass is deflect when a unit force is applied to any of these masses. Let me explore this influence coefficient by considering displacement of each mass as x1, x2, x3 corresponding to the masses 4m, 2m, m respectively. To find the first set of influence coefficients, we apply a unit force specifically to the first mass at 4m while keeping the forces on the other masses at 0. Let me see, that is, when we are applying a unit force at this mass and seeing the displacements, what will happen? We will have to use A11 equal to force by stiffness. So the spring which is connected to the 4m mass is going to be disturbed. So then what you are going to get? Simply force divided by the stiffness which is correspond to the 4m mass. So it is now 3k. Force is already unit force. So 1 by 3k we will get for A11, that is influence coefficient. Okay, since the other masses move by the same deflection, so by definition of influence coefficient, we can able to see that A12 as well as A21, A13, A31 also equal to 1 by 3k. Why? Because means what is A1 of 2? We are applying the same unit force at mass 1 itself and we are seeing any deflection in the mass 2. Mass 2 doesn't have any separate displacement at x2. It is once again the displacement of mass m only we have to accounted for this. So we are getting 1 by 3k. Then since the other two masses are going to be moved by the same deflection, so we are taking granted that A12, A21, A13, A31 equal to 1 by 3k. Now here is a key point. Because of this, mass and springs are connected in this initial scenario, other two masses will also move by the same exact amount of deflection as per the first mass. This leads us to important property to influence coefficient, that is deflection of mass I due to unit force at j is equal to deflection of mass j due to unit force at mass I. That's how we got A12 equal to A21. Now let's consider applying a unit force to the second mass with no force on the other masses. Now two springs 3k and K are put to extension by the second mass. Both are connected in series. So by using the series, springs are connected in series formula. 1 by 3K plus 1 by K will be equivalent to the equivalent value of 4 by 3K. So the stiffness here, it is already reciprocal. 1 by reciprocal of stiffness is there. So 4 by 3K will be, if we rewrite, we get equivalent stiffness of 3K plus K acting on the second mass 2m will be equal to 3K by 4. So the influence coefficient is nothing but force divided by stiffness. Already force is 1. So stiffness value, if you are substituting 3K by 4, it will be equivalent to 4 by 3K. And once again, if you are applying the influence coefficient property, A22 also equal to A32 and also it is equal to A23, because we are applying force only at second mass and seeing the disturbance at third mass. Like that we have to, the meaning is. So it is 4 by 3K. Now let's consider the displacement of the third mass. In this case, that is the third case, the problem states that the mass m covers the same displacement as a influence coefficient A22. This means that the deflection of the third mass due to a unit force on the second mass is also 4 over 3K that we seen just now. But let me go for the last category, that is finally we apply a unit force to the third mass with no other forces on the first mass and second mass. So what we will get, it is nothing but, since springs are connected in series, this is the last mass, we have to take into account of all the springs. So the unit force on the third mass extends the spring with the stiffness K, spring with the stiffness another K, and spring with stiffness 3K. Since this is pulling, if this spring is pulling, this mass also will move. So this K also will move, this 3K will also move. So to find the equivalent stiffness, we again sum the reciprocals of the individual stiffnesses. This gives us an equivalent stiffness where 1 by reciprocal K equals to 7 over 3K. Therefore, deflection of the third mass due to unit force applied to it itself, denoted as A33, is the reciprocal of this equivalent stiffness 7 by 3K. By systematically applying a unit force to each mass and observing resulting deflections of all the masses, we have successfully determined all the influence coefficients for the system, that is A11, A12, A13, A21, A22, A23, A31, A32, A33. Provide a complete description of the system's response to external forces. This analysis is a fundamental step in understanding the dynamic behavior of such mechanical systems. Next, we will see another example how to determine influence coefficients. Here we have another example which asks us to determine the influence coefficient for the given spring mass system. This system also involves three masses, namely the mass m, mass 2m, mass 3m, connected by a spring with stiffnesses 3K, 2K and K, arranged in vertical fashion. We will follow the provided solution to understand how the influence coefficients are derived. Let me get the solution by assuming, that is, we are applying unit force at 1, then getting the displacement. What will happen? If this mass is going to be applied force, only this stiffness will be come into picture. So force is unit, force is 1 divided by stiffness corresponding to that is 3K. So A11 represents deflection of the first mass due to unit force applied to it, and that is further equivalent to A12. It is the deflection of the same first mass due to unit force on the second mass. That means even though a force is applied on second mass, mass m stiffness is correspond to the same 3K. Similarly, A13 is the deflection of the first mass once again if the force is applied at the third mass. Since the first mass is directly connected only to the spring with stiffness 3K at the top, this is not horizontal, you have to see that it is at the top. Any force applied to any of the masses below it will cause entire system above that point to move as a rigid body. Therefore, a unit force at any of the masses will result in the top spring with stiffness 3K extending by 1 by 3K, causing the first mass to deflect by the same amount. Focus on the next mass, that is, if I am applying the unit force on second mass and arriving the deflection, then what will happen? This is the deflection once again on the first mass. So, if the same category, if I am applying the force on the second mass, deflection if I measure, it is same. Represent the deflection of the second mass due to unit force on the first mass, means it is going to be the same. So, it is 1 by 3K. So, unit force on the first mass will extend the same, it is 1 by 3K, causing all the masses below it to also move down by the same amount. So, A21 also equal to A31. But in the next case, you can able to see that this is force applied at the second mass and calculating displacement at the second mass itself. So, we have to take the springs which is connected above that, that is 3K and 2K both are going to be responsible if the force is applied at the second mass. So, since the springs are connected in series, we are using the springs in connected series, that is 1 by 3K plus 1 by 2K to get the equivalent stiffness, that will give you 5 by 6K, that you can substitute it. So, total deflection of the second mass will be summation of the extension of these two springs. The extension of the top spring is 1 by 3K, extension of the middle spring is 1 by 2K. Adding this together, we get and simplified to 5 by 6K. Also, we can see that the next mass, it is that if force is going to be applied at the mass 3, that is unit force at 3m mass, and deflection is going to be measured at the same mass 3, then what will happen? We have to take into account of the all the three springs which is connected above to the mass 3m. So, the considered thing A33 we can able to calculate means deflection of the third mass due to a unit force applied to it. A unit force on the third mass will cause all three springs to extend. The top spring extended by 1 by 3K, middle spring extends by 1 by 2K, bottom spring extends by 1 by K. Adding these extensions together, what will happen? We will get the equivalent thing as 11 by 6K. So, this is going to be the influence coefficient of A33. So, let me conclude the determination of influence coefficient, that is, by this step-by-step analysis, we have determined all the influence coefficients for this vertical spring mass system. Understanding how to calculate this coefficient is essential for analyzing the static and dynamic behavior of more complex mechanical systems.